Hello class. Welcome to chapter 5. This is section 1 and we're going to be talking about work today. So we have 4 different goals. The first is I want you to recognize the difference between scientific work and ordinary work as we think of it daily. We're going to define work by relating it to forces and displacement. I want you to be able to identify where work is being done in a variety of situations and calculate the net work done when many forces are applied to an object. What is work? What do you guys think of when you hear the word work? So just take a minute here, pause, and write down a few ideas. Go ahead and just hit pause and write it in your notes. What did you come up with? Well, maybe you came up with things like this. Your parents go to work each day to make money. Maybe it feels like work to do your homework. Or maybe working out or playing a sport feels like you do a lot of work, like running around and kicking a ball or lifting weights. All of those are common daily ideas that we think of when we hear the word work. And so in our daily lives, we tend to think of this as being something that takes energy or that we should or have to do. But in reality now, we're going to look at scientific work. So scientific work is defined differently. Work is defined as being done when a force causes a displacement. So throughout this slide, I'm using the color blue when we talk about forces, and I'm using the color pink when we look at displacements. So here I have a couple of examples. Maybe you're pushing a box, and you push on it with a force, and it moves. So we have a force and a displacement. Here, okay, maybe you're walking your dog and you've got a big dog. Maybe your dog is walking you. So you're moving this way even though you're pulling that way. In both of these cases, we have forces and distances, okay? I want you to notice here now that in both cases the force is parallel to the displacement. This is going to be important here in a minute. So force is parallel to displacement. So when you walk across the room carrying your book, it is not work. Okay, I'm going to say that again. Walking across the room carrying your book is not work. Not. Okay? And I want you to notice, it is because your force is pushing up and your displacement is going this direction. They're actually perpendicular. Okay? Anytime the force is perpendicular to the displacement, it is not work. And I know that seems strange because your arms can get tired holding your book, but it is still not work. But when you take that same book and you lift it off the table, right, you're lifting the book so the force is up and the displacement is up. Our force and placement are now parallel, and so you do get work. So force and displacement must be in the same direction or really parallel, okay? Because we could have the force pushing down and we would get the same effect because they're parallel. Now imagine you're picking up your textbook. Since you're lifting it, force is parallel to gravity, you're doing work. So how might we calculate the work that you do? Turns out that work equals force times displacement. Okay, so here I've written our numbers from the previous page. Okay, we have 0.1 meter displacement and a 10 Newton force. So if we multiply those, 10 times 0.1 is 1. And we have units of newtons times the meter. So we have 1 Newton meter. So what unit are we going to use? Okay. Well, like I just said, the units of work are force times displacement, so we get Newton and a meter. And when we multiply those two together, we're going to get a unit called the joule. We use the capital letter J, and 1 joule equals 1 Newton times 1 meter. And we spell joule Joule, and that is named after a scientist who did a lot of study on energy. So in our previous example, we found that we had a 1 Newton meter for lifting the book off the table. So that 1 Newton meter will actually be 1 joule of work done, lifting our book. Let's look at another example, okay? What if you are climbing a mountain? Now, if you were here in 8th grade, you climbed a Jiaoming Lake. And Jiaoming Lake is at an elevation of 3,310 meters, but the path there is roughly 14 kilometers long. So how much work did you actually do when you climbed up this mountain? Do we use the path distance or the height? Okay, so we got to think about what direction our force is here. Okay, when we talked about carrying the book, the displacement was in that direction, but the force was in this direction. And that's what we have going on here partially. Only now you have some displacement in this direction, and now we're going to add some in this direction, right? Because you end up at the top of the lake. So you have some in both directions. So what we want to use is just the displacement in the direction of the force. And you're doing work against gravity, so your force is going to be up as well. Now your force, you're lifting your own body. So imagine that the force that you're using that whole time is maybe 75 newtons to lift you and your bag up that mountain. That's how much you use. So then if the displacement, okay, which is that height again, is 310 meters, then we can multiply those. And when we multiply them, work equals force times distance, which equals our 75 newtons times our 3,310 meters. And when we multiply that out, the work done ends up being 248,250 joules of work. We'll often encounter large numbers of work like this, so we'll often switch this to kilojoules, which would be 248.3 kilojoules of work. And that would be your answer. We're going to look at one more example now, because what if we're pushing a box? And when we're pushing on that box, you can imagine the force here is at this angle, okay? But we know that that box is going to move in this direction. So how do we calculate the work done then? Okay. Well, remember this is net work, so even though we have some force of friction in this way, I'm going to count the force that we're pushing on as being the net force. Okay, so we're going to say the net force is 10 newtons, and that's what I said here in our example. So, we move the box a total distance of 5 meters. What is the work done? Well, we just want the component of work done in the same direction as displacement. So we're going to kind of draw a line here with the horizontal, which is our direction of displacement. And if this angle is 45 degrees, you're pushing exactly down there, then we can always use this equation, work equals force, okay, times distance, but then we're going to add, if we remember our triangles, okay, if this is our hypotenuse, this is our adjacent angle, so we're going to use cosine of our angle theta there. So it's going to be force times distance times the cosine of our angle. Now if we plug that in, we're going to get our force of 10 newtons times our displacement of 5 meters times cosine of our 45 degrees. And when we plug that all into our calculator, we get an answer of 35.36 joules of work that is being done. Our last thought here as we look at all this now is about the sign of work, because the sign of work is important It helps us understand the direction of the forces. So work is a vector, okay, and displacement is a vector. Work, however, is not a vector. But the sign of work still matters because it tells us whether the work is being done on the object or being done by the object. So it kind of gives us the direction of work in that we know which side is gaining or losing energy. So this example is from your book. You can see this in chapter 5.1. And they have these pictures here of positive work on this side and negative work on this side. And the reason they have two different ones on both of these is they want you to notice that pushing or pulling doesn't change the sign of work. It's not about pushing or pulling. It's about the direction of the force and the displacement. So if we look up here at this first example in the positive work column, you'll notice that the force is in that direction and the displacement is in that direction. Also, this one below here, the force is in that direction, displacement is in that direction. So when force and displacement are in the same direction, that is when we get positive work. Now if we look at the other half of our example over here on this side, okay, again, whether it's pushing or pulling, if we have the force in that direction, displacement opposite, or we have a pushing force in that direction and displacement is opposite, both of these we have force and displacement are opposite. They're going in different ways. So whenever force and displacement are opposite, we get negative work happening. Let's look at a couple examples here and see if you can determine whether something is positive or negative work. So we're going to look at this example here. Okay. What we have, we are going to look at what the work done on the second object is. Okay, so the road exerts a friction force on a speeding car. That's our second object. And that car is sliding to a stop. So you can see kind of the skid marks here. So remember, friction is always opposite of motion. So if the car is going this way, that's our direction of displacement. Our direction of force, friction, is opposite motion. So our friction force is going in that direction. So displacement and friction are opposite directions. That means we have negative work going on. Let's look at another example. This time, a rope exerts a force on a bucket as the bucket is raised up a well. So I have a picture of a well here in our bucket. So if we think about the direction of the force, it's pulling it up. So our force is up. And the displacement, the direction the bucket moves, it turns out, is up too. So this would be an example of positive work because both the displacement and the force are in the same direction. So we're going to look at one more example now. And I want you to think for a minute and see if you can figure out what direction things are going. So the air is exerting a force on the parachute as a person falls towards the earth. So just pause here for a minute and think about it and see if you can figure out which directions things are. Hopefully you hit pause and we're able to think that out. So let's look at what it says here. Air exerts a force on the parachute. Well, the parachutist is moving downwards. Okay, so we know he's falling, so that's our displacement. And air exerting force on a parachute is air resistance, and that is pushing up on the parachute. So our force ends up being up. So force and displacement here are opposite, not the same way, which means that we get, dun 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 dun, negative work. So let me know if you have any questions in class or online, and I will see you in class. Thanks for listening.